Hello and welcome to the next unit review video. Today's video is going to focus on Unit 3 linear functions, equations, and their algebra. So let's first give an overview of what to expect in this video. Okay. First thing to expect is that we will do lesson overview, just like we did before. Then I'm going to briefly show you the standards that are going to be assessed in the Regents exam. In this video, I'm going to show you some formulas, so make sure you have that separate sheet for the formulas handy. And then I'm going to get into the topical reviews in this unit before summing up the most important key features of this unit. Don't forget to pause the video as you go along to write down anything you need to. In Unit 3, we had 7 lessons. And the focus, as I mentioned, was on linear functions. However, when we looked at average rate of change, we applied that formula that we're going to be looking at to any type of a function, not just linear functions. But that was pretty much the only one here we were dealing with nonlinear functions. And there are 5 Common Core standards associated with this unit. Essentially, one of them is solving a 3x3 system of equations, or solving them graphically. So 2 equations, given the graph, use the calculator to find the intersect points. Then calculating the average rate of change. Okay, you could be given either a table of values, or the graph, or the equation. Okay. And they may involve any kind of function. Okay, polynomial, exponential, logarithmic, trigonometric functions, and so forth. Okay. And also, next thing we should be able to do is construct a linear function given the graph or description of relationship of the 2 pairs of variables. Interpret the parameters of a linear function, such as the slope, y-intercept, domains and ranges, and lastly to find the inverse of a line. So let's first look at some formulas. Okay, the first formula we're going to look at is direct variation. That occurs when you have essentially a line that passes through the origin. Y is equal to kx. That is the formula for direct variation, because if you divide y divided by x, you get a constant. Okay, it's a constant relationship. Okay, constant slope. We're going to look more into depth with that. Look more in depth with that in a moment. Average rate of change is we find the change of a function over the change of a certain interval. Okay, and that is found by evaluating the function at 2 variables and subtracting them, divided by the input variables subtracted. So this is the rate of change formula. And there are a couple forms of lines that we looked at. Slope-intercept form is the most common one, y equals mx plus b. And point-slope form we saw in geometry and also this year. That's where we have y minus k equals m parentheses x minus h. Now note, with the point-slope form, you might see it written as y minus y1 is equal to m times x minus x1. Okay, they're both perfectly fine. Let's look at some topical reviews. Direct variation. So examples of direct variation. So that's the formula, as was mentioned, is y equals kx. So examples of direct variation would be something like this. Y equals 7x. Y equals 1/2 x. Or maybe y equals something like maybe radical 5x. Some number times x. Because the rate of change, or this, the constant of variation, should I say, is going to be 7 if it's equal to 7x. Meaning if you take the output value divided by the input value, you're always going to have a value of 7. Y divided by x, that gives you a value of 1/2. Y divided by x gives you a value of radical 5. Okay, so it doesn't have to be integers or fractions, it could be irrational. Okay, as long as it's some number times x. So some examples that are not direct variation are whenever you have something we have in y slope-intercept form where you have a y-intercept other than 0. So for instance, y equals 3x plus 2 is not a direct relationship, okay? Because you cannot get a constant when you do y divided by x. That does not equal some kind of constant. So if you're asked to test to see if things are directly related, see if you can find the equation, and if you get something that looks like this, then you know you have a direct variation. Let's look at the rate of change formula. Okay, so again, we have a formula, let me write this again, delta f over delta x, change of x over change of f over change of x is going to be f of b minus f of a over b minus a. So we already wrote that formula down. Okay. So let's just say, for instance, that we have a function, f of x equals, let's say, x squared minus 4x. I want to know what is the rate of change for the interval -1 is less than or equal to x is less than or equal to 6. What I'm going to do in that case is I'm going to evaluate the function at -1 and I'm going to evaluate the function at 6. Now note, I'm giving a function in terms of an equation, but you could also be given a graph or a table, and from those you should be able to find out the evaluation of those functions by examining them. Okay, but function in the equation form is most common form. So just plug in -1. That gives me +1 plus 4, which is 5. Evaluating 6. So it gives me 36 minus 24, which gives me 12. Okay, so if I'm going to find the average rate of change of this function over that interval from -1 to 6, I'm going to take my f of, and this is my a, this is my b, okay, -1 is my a, 6 is my b, f of 6 minus f of -1 all over 6 minus 1, minus -1, so it becomes +1. So I get 12 minus 5 over 7, 7 over 7. So the average rate of change here is 1. Okay, that's just an example of doing the average rate of change. Now, with this unit, we're focusing on linear functions. So what's really important to note is that for linear functions, the rate of change is constant. No matter what interval you're looking at, you're always going to have the same exact rate of change for a linear function. For any other type of function, absolute value, square root, radical, polynomial, trig functions, you're going to have different rates of changes for different intervals. Okay? So if I were to evaluate my given example for some other than -1 to 6, maybe 0 to 6, I would have had something like 12 over 7, which is different than 1. Okay. Or 12 over 6, sorry. Okay, pause the video, write down anything you need to before going on to the next slide. So there are several forms of a line with slope-intercept and point-slope form. Okay. Given a line, given a point and a slope on a line, say we're given the point 5, 7, and we're given the slope of the line is -2/3, we're going to be using the point slope form because that's what we're given, a point and a slope. So recall This is the point-slope form. So my h and my k are going to be my x and y values of my point, and my slope is my m value. So the equation in this case is going to be y minus 7 is equal to negative 2/3 x minus 5. That's how you find the equation given a point and a slope. Use the point-slope form. Now you may be asked to find the equation of a line parallel to a given line or perpendicular to a given line. What you really need to know is the slope of the original line. And you have to know that for both finding the line of a parallel relationship and a perpendicular relationship. So you need to know it for both of those. Because parallel lines have equal slopes. Parallel lines have equal slopes. Perpendicular lines have negative reciprocal slopes. So I'm going to use the same example that I had up above with the 5, 7, and negative 2/3. Let's say I want to find the line parallel that goes through the point 5, 1. Let me do a little different. Okay, through maybe 7, 4. Okay, yeah, I'll use different numbers. Parallel through this point, 7, 4, and we're going to do the one perpendicular through 7, 4. Okay. Now, if you're given the equation, then all you have to do is just rewrite it in the form y equals mx plus b, get y by itself. That will allow you to find the slope of your original line. Okay. Let's just say we already found that the slope of the original line is the negative 2/3 from that first example. The parallel slope is going to be the same thing, negative 2/3. So if I'm going to write the equation, I'm going to use the point slope form because I have the point I'm going through and my parallel slope. So it would be y minus 4 is equal to negative 2/3 x minus 7. My perpendicular slope is going to be the negative reciprocal, means I have to flip it, make it 3/2, and negate it, so it becomes, in this case, positive. Again, I have a point and a slope, so I'm going to use the point slope form, so y minus 4 is equal to 3/2 x minus 7. Okay, and that's how you find the equations of parallel and perpendicular lines. Find the equation of find the slope of the original line, and then use the point slope form. Now you might be asked also to find the solution to linear equations graphically. Okay, whenever you're given two equations, what you want to do is get y by itself in both of them if they're not already written by themselves. So you can put in the equations into your calculator. Of course, being careful about parentheses when you put it in, especially if you have fractions and negative values and so forth. Okay, just be careful about it. So, two intersecting lines, you're going to graph them, and you're going to have something that looks like this. Okay. And this works, by the way, for nonlinear equations as well, as long as they intersect at some point. You can use your calculator after you hit graph. Make sure you have the appropriate window so you can see them. So you may have to manipulate the window in order to have them graphed. Sometimes the window is given to you on the axis. Looking at the graph, see where they intersect, then you want to do, in your calculator, second, press that button, calc, which is located where it says trace. Second, calc. And one of the options is going to be intercept. On my calculator, it's 5. What you're going to have to do is you're going to have to choose the first curve, hit enter. You can choose the curve by hitting the arrow buttons between several equations. But if you just have two equations, you just have to hit enter. And then you have to choose a second curve. And you do that by hitting enter. And then you have to choose a guess. So you have to scroll the point, the little plus sign, make it move along the graph until it gets to the point of intersection. So maybe the point would be here, moves up the graph until it gets to about right there. Then you hit enter, and it should give you the coordinate pairs of the intersection point. Probably in the form of x equals some number and y equals some number. Okay. That gives you the solution to the system of equations graphically. Now if you want to find the interval of x values for one equation between certain two y values, or greater than or less than one y value, what you're going to do is in y1 you're going to write the equation of the line. And what you could do is in y2 and y3 write the value of the two y values you want to be between. Say you want to be between 6 and 10. So I would put y2 is 6, y3 is 10. And it'll graph both those. And say you want to know the values between those two outputs. So what values of x give you all the values between those two outputs? You're going to do the exact same thing as up above. Second calc, intercept, first curve, second curve, guess. First curve will be your y1, but second curve, you'll have to maybe, for the second intersection point, use the up and down arrows, or the left and right arrows, in order to get to, on the top of the window it should say y1, y equals 2, and so forth. Okay, that allows you to choose the equation that you want. Okay, and then you will get your 2 points. Okay, so you'll have to do it twice, once for that intersection, once for the second intersection, and then I'll give you 2 x values. Another focus in this unit, which we kind of saw a little before, was the inverse relationship of linear functions. Okay. And recall with inverses, all you have to do to find them is just switch the x and y, and then solve for y. So if I have an equation such as y is equal to 3x minus 6, I'm asked to find the inverse. By the way, it could be given in function notation. 3x minus 6 is equal to f of x. I just have to switch the x and the y. So I'm going to write x is equal to 3y minus 6. Then solve that for y. Add the 6 to both sides. X plus 6 is equal to 3y. And divide both sides by 3, which eventually gives me y is equal to x plus 6 over 3, or 1/3 x plus 2. So you can write your inverse function as 1/3 x plus 2. You can write it as y equals x plus 6 over 3. Both are fine. Or you can write it using the function notation. So remember, inverse function notation has f to the negative 1 of either one of those. Now, for most lines, you're going to have an inverse function as a line that is also a function. Okay, there's only one case really where you don't have a function. And recall that in order for it to have an inverse function, it needs to be 1-to-1. Okay. Now every function has an inverse. It's just whether or not the inverse itself is a function or not. It must be 1-to-1 in order to have a function inverse, or an inverse that is a function. The only case where it's not 1-to-1 is if you have something like y equals 3. Because clearly that does not pass the horizontal line test. The inverse of that function ends up being x equals 3. So it has an inverse. But notice, if I were to graph x equals 3, it definitely fails that vertical line test. Okay, so it's not a function. So for lines, you have something that's not going to have an inverse function if you have y equals some number. Okay, that in itself is a function, but its inverse is not a function. Okay. And another thing you're going to be asked to do with the inverse functions, and this applies for other functions as well, but let's say we know on f, we know that our input of 2 gives us an output of 5. Or in other words, we have the point 2, 5 on the graph. The x value input is 2, and the output y is 5. If I want to know a point on the inverse, I just switch the x and the y. So the inverse, write that again, to the -1. The inverse of the output of the original must be the input to the original. So you have to just switch it, which means that the point 5, 2 is on the inverse. Okay. So you just got to switch the x and y coordinates. So if you have the point 6, -1, that means that -1, 6 is on the inverse. Piecewise functions is something that we started looking at in this unit more extensively. And you should be able to do two things with these. From the graph, be able to write the equation of the piecewise function, and from the piecewise function, draw its graph. So basically what a piecewise function is, you have some function that's split up over different equations for different intervals of inputs. So you could see something like this. 3x plus 5 is one equation. Maybe 1/2 x minus 7 is another equation. And maybe -3/4 x plus 7 is another one. Now, to make it a function, you can only have one output for each input in order to be a function. So, you have to encounter elements of the domain that do not repeat. So, for instance, this 3x plus 5 might be used for the domain x is less than -5. The 1/2 x minus 7 might be all the values from -5, including -5, all the way up to maybe 3. And then the last one might be between positive 3 and 10. So you don't have to cover the entire domain, but as long as you don't have repeating values. So if you have x values that are the same, you just have to make sure that their signs, only one of them has an equal sign. Okay. You can't have something like x is less than or equal to -5, or -5 is less than or equal to x less than 3. You can't have that kind of situation, because if I said evaluate the function at -5, you don't know whether to use that line or that line. Okay, you have to have only the domains that do not have repeating elements. Now what I would do for this function is, on the graph, I have -5, 3, and 10. Okay. 3x plus 5 less than -5. So if I find a table of values, okay, what I would do is I would do something like this, maybe like -7, -6, -5, -4, -3. Okay, and then let's skip a few, all the way up to maybe 1, 2, 3, 4, and so forth, and then maybe 5, and all the way up to 10. Okay, I can create a table of values to help graph this. If I were to evaluate -7, it's going to go into that first one because it's less than -5. -21 plus 5. That was my cat, he just sneezed. Hopefully you didn't hear that. -21 plus 5 is -16. -6 goes into that first one still because it's still less than -5. -18 plus 5 is negative 13. Now negative 5 only will go into the 1/2 x minus 7. But we still need to evaluate it at the first one because we need to know where it's going to end at an open circle. Okay, so I'm still going to evaluate, but I'm going to put it in parentheses to help me know that it's not actually going to be a point on that line. Okay, plug in negative 5, I get negative 15 plus 5 is negative 10. So negative 5, negative 10 is going to be an open circle on the graph. Okay, so you're going to have something like this. And at that point it's negative 10. Now at negative 5 though, you need to still plug it into here. So negative 5 divided by 1 times 1/2, or divided by 2, subtract 7, that gives you negative 9.5. So at the value of negative 5 as an input, you really have negative 9.5. So maybe like right there. And then you can continue filling the table out. So negative 4 into there gives you negative 2, so it gives you negative 9. The next one gives you negative 8.5, so forth. Okay. And then at 3, at 1, we have to find out what happens up to 3. So at 1, we're still using that 1/2 x minus 7. So 1/2 x, so that gives you 1/2 minus 7. Negative 6.5. Okay. That's 2. We get 1 minus 7, which is negative 6. And again at 3, we're not going to be actually on that second line, but we need to still find out that value because that's going to be an open circle on the graph. So at 3, I get negative 5.5. And again, I'm going to put that in parentheses just because I know that's actually not on the graph. Okay, it's just an open circle. At 3, so that means that we go to negative 5.5, so maybe about like right there. It's going to be an open circle. Now, of course, my scale on this is kind of horrible. Okay, but just keep that in mind. Okay, we have a closed circle at negative 5, open circle at 3. Now, for the remainder of the graph, it's going to be between 3 and 10, including both those values. So we have to find the value at 3. We're going to plug it into here. So 3/4 of negative 3 plus a 7 gives us 4.75. Now, at 4, that gives me a value of 4. Okay, and if I were to go all the way up to, notice if I did 5, negative 3 times 5 divided by 4 plus 7, that gives me 3.25. Go all the way up to 10, negative 3 times 10 divided by 4 plus 7 gives me negative 0.5. So that means at 3, I'm going to start all the way up at 4.5, or 4.75. It's going to be a closed circle. And I'm going to go down to negative 0.5. It's going to be a closed circle as well because it is equal to in the domain. And this is my graph of my inverse function. And of course I would label the axes as f of x and x because I'm giving it in terms of f of x. Okay. So given a piecewise function, this equation, you should be able to graph it. Now if you're given the graph of a piecewise function, so let me clear all this off. Let's say I'm given the graph. Okay. I'm given the graph of maybe g of x, and I'm given something that looks like this. Okay. Let's say that x value is negative 3 and this x value is 5. Okay. What you need to do in order to find the equation, first notice there's 3 different parts to this graph. So my function g of x is going to have 3 different equations over 3 different intervals. You have to find the equation for each part. Now what you may have to do is use the graph, either find 2 points on each part, if it's a line, to find the slope of the line. Okay, let's just say we find out that the slope of the first one is 2/7. Okay, x. You have to find out what the y-intercept is, so you may have to use the graph to find out what that y-intercept of that piece is going to be. Now notice that will not actually, the y-intercept will not be on the actual function because you had to draw it to get there. But let's say the y-intercept ended up being 10. So it would be plus 10. But you have to indicate the domain that you're going to use that piece for. So it has an open circle at -3, and it's less than, all the values less than -3, so it's going to be x is less than -3 is your domain. Then you look at the next piece. This one happens to cross the y-axis, so maybe it crosses the y-axis at 2. Okay, and let's say we found out the slope of that part ended up being, choosing 2 points, 5/3. So it's going to be 5/3 x plus 2. And the domain where that piece occurs is going to be between -3 and 5, and including those values. So it's going to be -3 less than or equal to x less than or equal to 5. And for the remaining piece, the third piece, again, we have to do like we did in the first one, kind of extend it to find out where it intersects the y-axis. Okay. Let's say it intersects the y-axis at 17. And let's say we also calculate the slope, finding any 2 points on there, as being -4/3. Okay, so it's -4/3 x plus that y-intercept of 17, if you were to extend it. And that is for all values of 5 and above, but not including 5 because it is an open circle. So it's going to be x is greater than 5. And that's how you find the equation of a piecewise function given its graph. Let's move on to solving systems of 3x3 equations. Now this is most likely going to probably be an open response question on the Regents exam. So it's really important to know how to do this step by step. And the way we solve 3x3 systems is to make the 3x3 and turn it into a 2x2 by eliminating a variable. Okay. So turn it into a 2x2 by eliminating one variable. So if you have x, y's, and z's, or maybe a, b's, and c's, or any other 3 letters as variables, you want to eliminate it to just 2 of the variables. So you're limiting the same variable in the first step. Okay. Then you can solve that 2x2 by making a 1x1 by eliminating another variable. And what that does is it gives you just one variable with one equation that you can solve for that variable. Then what you do is you use that solution to go back to one of the 2x2 equations to solve for the second variable. And you're going to use those 2 solutions that you got into one of the 3x3 equations to solve for the third variable. And there you have your answer. Okay? So eliminate a 3x3 to a 2x2, 2x2 to a 1x1. And then you're going to kind of work your way backwards to find the solutions to the variables. Okay. So even though we're calling these variables, there's only one value that will work for all of them. Okay. But we just don't know what they are. So, solving a system of equations. The easiest way to do this is to start labeling your equations. Okay. I have 3 equations, so I'm going to label them as A, B, and, not B again, and C. If I label them A, B, and C, what I want to do is I want to find the easiest variable to eliminate. If I look at the x variables, the coefficients of the x variables, I have 3, 4, and 4. They're all positive, all the same sign, and they're all kind of strange numbers. Okay, there's no easy way to multiply one equation to eliminate with the other one. I have to do it with fractions. I could multiply a by -4 and b by 3. That will give me -12 and +12, which will cancel. But that's a little bit of work. Okay, so let's not worry about that. If I'm looking at the z variables, okay, I start seeing some opposite signs, because it's better to see opposite signs because you can multiply by just positive integers, keep all the signs, and then eliminate that way. But I noticed that there's 3 different numbers. A 1 in equation C, a negative 2 in equation A, and a 3. So I'd have to be multiplying by several things. So that's a little bit easier to deal with. You could do this easy if you wanted to. What I'm noticing with the y's is I have opposite variables, and I have just two numbers to deal with. So that's going to be the easiest way to eliminate a variable. So eliminate the y's in this case. To eliminate the y's, what I'm first noticing is if I look at equation A and equation C, I notice I have a plus y and a minus y. So if I just add those two equations as they are, they will eliminate the y's. So the first step I'm going to do, and I'm going to organize my work in a nice neat way. So as you see this, I would suggest you eliminate that you show your work in a similar way. Identify the two equations you're going to be adding together. So I'm going to be adding A and C and rewrite them. So I'm going to do 3x plus y minus 2z is equal to 12. So I'm going to have to write that z a little better. 2z equals 12. I'm going to write equation C, which is 4x minus y plus z is equal to 3. And I'm going to add those together. If you can, it's always better to add than subtract because you have to be careful about signs. Okay. So let's add these. Add the 3x and the 4x, that gives me 7x. Add the y's, they cancel. Negative 2z plus z gives me negative z is equal to 12 plus 3, which is 15. Now I eliminated the variables to create one equation, but I have to have a system of 2 by 2, so I need another equation. So I'm going to choose another pairing. I already did A and C, so it's the other options that we have are A and B, or B and C. Okay, those are the two options that we have. Now I'm looking at this, and I'm saying, well, A is positive, and B is negative. So if I look at those two, I just have to multiply one of them by a constant and keep all the same signs and add them together. If I were to choose B and C to eliminate the y's, maybe I have to eliminate the same variable, you would have to multiply by a negative in one of the equations. Okay, so A and B looks like the best way. And if I multiply A by 2, that gives me a 2y. So what I'm going to do is I'm going to do 2A plus B. Okay, I'm indicating what I'm doing with the equations, 2A plus B. So I have to multiply all the terms in equation A by 2. That gives me 6x plus 2y minus 4z equals 24. And then I'm going to combine that with equation B, which is just 4x minus 2y plus 3z minus 3. Okay, let's add those together. That gives me 10x, the y's cancel, minus z is equal to 21. This gives me a system of 2 by 2 equations. Okay, so this 3 by 3 essentially became into 2 by 2 with the equations 7x minus z equals 15 and 10x minus z is equal to 21. So the system of 3 by 3 became a system of 2 by 2. Now let's solve this for either x or z. You want to use the same strategy, find out the one that's going to be easier to eliminate, and notice that the x variables, you have different numbers. The z variables have the same number, even though they have the same sign, you can still eliminate those. That's probably the easiest to eliminate. So I'm going to label those two equations as D and E. Okay. Now I have to eliminate one of the variables. In this case, I'm choosing to eliminate the z's, and I can do that by subtracting them. So I'm going to do D minus E. Notice you kind of think about this as D plus negative 1 times E. Okay, and if you want to do it that way, that's probably the easiest way to do it, to keep it consistent with addition. So I'm going to multiply everything in E by negative 1 to change all the signs. So I have D, which is 7x, minus z equals 15. E, I'm going to multiply by negative 1, which gives me negative 10x plus z is equal to negative 21. And now let's add them. 7x minus 10x gives me negative 3x. The z's cancel. 15 minus 21 gives me negative 6. And notice now I have my 2 by 2 became a system of 1 by 1. Negative 3x equals negative 6. One equation, one variable, and that's something that I can solve. Okay, if I divide both sides by negative 3, I get my x value must be 2. There's one solution. Now, to solve for the next variable, I'm going to go back into my 2 by 2's, choose one that's going to be easy to work with. They're both equal difficulty, so it doesn't really matter which one I choose. I'm going to choose the 7x minus z equals 15. Okay, so I'm going to rewrite that. 7x minus z is equal to 15. Now I know my x value has to be 2, so I can plug that in for x. So 7 times 2 minus z is equal to 15. Again, we have one variable. 14 minus z is equal to 15. Subtract the 14, negative z is equal to 1. Divide by negative 1, z must be negative 1. Okay, I'm going to kind of, just because I have limited space, I'm going to go into this area right here, okay, to continue solving this problem. Okay. Now I have z is negative 1, and I have x is 2. I just have to find out what y is. And I'm going to choose one of the equations in the original problem. Now what I'm noticing is that y is positive in equation A, and I'm solving for y, so I'm going to use that one. Okay, so I'm going to copy that down. 3x plus y minus 2z equals 12. Now I know that x is 2 and z is negative 1, so I'm going to substitute those values in. 3 times 2 plus y minus 2 times negative 1 equals 12. Alright, and let's continue solving this by reducing the terms. 6 plus y plus 2 is equal to 12. Combine like terms, y plus 8 is equal to 12. Subtract 8 from both sides, y is equal to 4. So there's a couple ways you can write your answer. Okay, one way is as a coordinate point, which since we have 3 variables, it's going to be an x comma y comma z. So it's going to be 2 comma 4 comma negative 1. That's one way to write the solution. Another way to write the solution is as x equals y equals z equals. So you can write the solution as x equals 2, y equals 4, and z equals negative 1. Both are perfectly acceptable ways of writing your answer. As a coordinate pair, or in this case a coordinate triple, or as x equals y equals z equals. Whew, that's a lot of work. So this might be a good 6-point question on a Regents exam, or maybe even a 4-point question. Probably not a 2-point question, but at least one of those two. Okay, pause the video, write down anything you need to. Alright, now this video is fairly lengthy, but I provided some examples for you so you can see how to solve some of the problems in this unit. Okay. But the most important thing you should be able to do from this unit is to use the average rate of change formula to find the average rate of change over a given interval of values. You should be able to easily solve a system of equations graphically. You should be able to find the equation of the inverse of a linear function algebraically. Given the function, find the inverse. Find a point on, or given a point on the function, give the point of the inverse on the inverse of the function. Let me say that again. Given a point on the function, find the point on the inverse. Basically switching them. So if you have 5 comma 2, you know that's 2 comma 5 is on the inverse. Okay. Whew. And I don't want to re-record this video in order to change that, so my apologies. Okay. Now the last thing, a few things, is to write the equation of a piecewise function given its graph, or graph piecewise function given its equation, and solving a system of 3 by 3 equations algebraically. Thank you for watching. Hopefully you've taken some good notes so you can have some nice review for the Regents exam.